Okay, our next and last speaker is Manfred Broy from TU Munich. He's known for his work in basically almost all areas of software engineering and systems engineering, from requirements over software architecture, components, modeling, and so on and so on. Manfred got his PhD in 1980 from TU Munich, and then after spending some time in Passau, he became a professor there in '89 and has been there ever since for the last 25 years. He has won numerous awards. To mention just a few, he won the Leibniz Prize by the German Science Foundation. He's a Max Planck Fellow, and he has numerous Best Paper Awards and other awards. So thank you very much for coming, and we look forward to your talk.
Okay, thanks a lot. Thanks for still being with us in the last talk on a Saturday afternoon. I will slightly change the topic because I would like to look a little bit at reliability from a more general point of view. If my machine would do the way I would like it to do. It doesn't. Very good mood. I think it looks better. Okay. I want to switch the topic a bit because we have seen a lot about how you treat programs. In particular, if you look at the execution of programs, if you look inside the structure of programs, and this is what we studied for a long time, we have this concept of computation, which is, of course, the concept of Turing machines. And of course, there's a lot of interesting work to do. I really enjoyed the talk so far. But I will switch a little bit to not looking so much at program, but rather to look at systems, and in particular systems where we have a lot of software in them. But these systems are connected to the physical world, and the physical world is a bit different than what we observe if we just look at inside the machine. So we need a coherent model for understanding how a system interacts with the physical world. So I will show a little bit about the work we do to model those interactions between systems and their, what I call, context. I think the notion of an interface is in particular important to deal with such systems, and we have to think about interaction, about time, architecture, state, and in particular, I will take some time to deal with probability, with data and event flow. And of course, we need a slightly different or generalized notion of computation, namely Mealy machines. Of course, we can get back a lot of ideas from computability of Turing machines for them, but we get additional things to look at. And this is in particular important if we want to look at dependability. And if we look at correctness and reliability, which is the topic of the workshop we have here, of course, we should understand what correctness and reliability is about. And we have not heard a lot about specification so far in the workshop. And you cannot talk about correctness without specification. So the first thing you have to look at is what are the specifications you look at. And of course, it's again completely different story whether you look at specifications at the level of programs, where you're interested in looking at a piece of program and then understand which specifications a program fulfills, or whether we talk about specifications about system behavior. And also reliability needs notions of correctness. But of course, if you look at reliability, then it becomes much more tricky because in a certain sense, it's not so simple anymore that you have a black or white understanding of specifications and correctness, because now you have to talk about time, about probability, about precision, and you have to deal with the uncertainty of the real world. And this is a step where you go from a logical understanding of correctness. A program is correct, yes or no. You go to a more, say, unsharp notion of correctness, where you can then talk about correctness in the sense that you say a system is correct to a certain degree, with a certain probability over a certain interval of time, or correct in some fuzzy way. And this is really a challenge which has to do with issues like uncertainty and probabilities. So let's just look to start with at understanding these different ideas about correctness. The first one is, of course, simple. If you look at sequences or streams of, let's call it output, and we have a set of streams which characterizes a set of correct output streams or sequences, then we can say a sequence, a stream, T prime is correct if T prime is in a set of correct sequences. So that's straightforward. And we can generalize it, of course, also to sets. But sometimes it's interesting to talk about an output that is correct to a certain extent. And perhaps one interesting question is to compare outputs, whether an output is more correct than another one. And of course, if you look in practice situation, of course, people often say, this is a correct program, this is now more correct than the other one. Also, from the correctness theory in a classical sense, this is not meaningful. But now we can introduce what could be a distance, a mathematical distance, and then we can ask whether a output sequence T prime is more correct than an output sequence T double prime by using this formula. We ask the minimal distance of the output T prime to a correct output, and we ask the minimal distance of T double prime to a correct output, and we say if this distance is closer than the other one, then it's more correct. So we get a more general idea of correctness. And of course, we could also go on and talk about correct with a certain probability. So we could say, what is the probability that output T prime that we observe is a correct one? And we could say we would like to see a probability which is above 90%. Or we could even generalize that and say the probability that we get an output which is correct to a certain extent, which is below 0.1, whatever 0.1 means, is above 90%. And so we get a much more weaker or more flexible way of talking about correctness. We could even go a step further and now go to fuzzy logic and talk about output which is roughly correct, and then we could even be in a situation where there's output which is called correct and not correct at the same time. But I will not go into fuzzy logic, which is another branch you could look at. We have to go in that direction, of course, if we want to capture classical notions of dependability. At the beginning of the week, I was at a workshop in Stuttgart on functional safety in cars. And then, of course, all these notions are around, like availability, reliability, which is in the title of the workshop, safety, security, maintainability, so a number of quality issues there we want to deal with. And the question is, what do we have to do to change our notion of, and I will not talk about so much about programs, rather about systems. How do we have to change our notion into a system and its behavior to be able to deal with those issues? Here, this picture should give you a little bit what I'm interested in. I consider a system, and if you like, you could think about a system as a car, or you could think about a system as a cash machine. And these systems are always running in a kind, what I call the operational context. So they are connected to other systems. For instance, the car could be connected wireless to some kind of a maintenance system of the OEM. It is connected to the physical world. The car is, of course, connected by its wires to the physical world. It can connect it also to other cyberspace issues, and it's connected over man-machine interaction devices to human interaction. I don't care so much about all these different things. Of course, if I would be careful, I had to think about that some of this interaction is no longer discrete interaction, we are no longer really in the field of digital devices, but we have also to look at continuous input and output. But I will not do that in my talk. I keep to talk about discrete systems. And here I give you my view what a discrete system is. And I say a discrete system has a boundary, which is very important because I have to understand which are the observations about a system, and that is fixed if I fix a boundary. And if the boundary tells me what is part of the system, what is outside the system, what I call part of the context. And having fixed the boundary, I already have fixed the interface. The interface is the description in which way the system is going to have some relationship to its context. And if you think in terms of behaviors, we can understand that by two steps. First step is what are the principal ways of a system interacting with its context. I call this a syntactic interface. So if you take a cash machine, it's obvious. You have a number of buttons you can press. You can put in cards. You can look at the display of the cash machine. That would be the principal interactions. But of course, if we talk about behavior, we are also interested in the logics. So what is a sequence of interactions which is possible, and what is a sequence of interaction which makes logical sense? I will a bit talk also about the architecture of a system, which is, in my point of view, a decomposition of the system in a number of subsystems and the description how they are related and interact. I will not talk about states, but I will show a relationship to quality profiles, and I will not talk about data models because they are quite well understood and simple. So if we look at a system, we get a number of views. We get the operational context view, and I call it CIB, context interface behavior. That's the behavior of the operational context. The interface view is the system interface behavior, which I call SIB. And if the system and its operational context work together, of course, we get observations and architectural view. And I give you a picture for that. This is classical if you study, for instance, safety. If you study safety, you have the system interface behavior, the context interface behavior, and I will show you later the formal operation. If you put them together, it's just composition. So you do a composition of the context and of the system, and doing the composition, and in my case, composition is similar or equivalent to logical and then to be able, for instance, to talk about dependability issues, you, of course, look at the observations. The observations could be seen in the interaction between the system and its context. And of course, we would be interested that we observe no failures, whatever failures are. And now our logical requirement for a dependable system would be if we take all the properties of the system we have specified, and if we take all the properties of the context we have captured and specified, these are assumptions about the context, these are requirements about the system, and if we take these two together, we can conclude from that there are no failures observable. So that's the idea. Now let's go to a system model we are working with for quite a while. Some of you will have seen that. I will not go very deep into that. I will just show you how to use now such a system model to be able to address the issues I'm interested in. The system model is very simple. It has, the system has a boundary. The syntactic interface is given by the names of the input channels and their types, and the names of the output channels and their types. This already describes completely the syntactic interface, because from there you can see what are the actions you can do with the system, because either an action is the system gets some input over a channel of that data type, or it produces some outputs. This is a fairly general model. You can model a lot of stuff by that. And then we have to talk about behavior. And in behavior, I use a notion of the stream. And the stream in that case is a timed stream, so it's a mapping from the naturals. The naturals characterize the time. A simple way to think about it is that you look at time intervals. Each interval gets a natural number, so you have the first, second, third, and so on interval. And this is now you have these intervals, and in each interval at a channel you can observe a finite sequence of messages. Could be empty, then you have no message in that interval, but it could be arbitrarily long, because you don't want to have any assumptions about how the, the frequency of the messages relates to the chosen intervals of the time. Having that, of course, it's easy to talk about, I call that an interaction history. An interaction history gives for a set of channels, for each channel such a stream. Of course, I should take typing also into account, but for simplicity, I don't mention that explicitly. And then we can talk about interface behavior. And interface behavior, and that's very important, is thought of as being a function. It's a function that takes input histories at input and produces for each input history, it produces or specifies the set of possible output histories that are possible in that case. So this is rather straightforward. So we have our discrete logical system model, and we have to, of course, now to think about what I call strong causality, because if we would take this model as I presented it here, we would be able to write nice specifications of systems which predict the future. Because we could write, or we could deal with behaviors where there is some output at a time t, which depends on input, which comes only later. And this is exactly what we don't want to do. So we introduce an additional logical rule. I will not go into details to explain that rule, but just to give you the idea. The idea is it explains that the output until time t plus 1 must only depend on the input until time t. And this is exactly what you would expect as a proper time flow in the system. And then we have a model with a number of characteristics. It's modeling interface behavior. It uses causality for modeling time flow, which is also interesting because we can use proof principles based on that. We can talk about system time and physical time. When we deal about this different understanding of time, we can talk about time requirements and execution time. We can do context modeling, which I think is in particular interesting for cyber-physical systems. We have to deal with non-termination because systems run without time limits in general. And then we can talk about issues like functional safety, security, and reliability. But however, to do that, of course, we need probabilities. So I will introduce probabilities a little later. But before doing that, let's just look at specifications. How can we now write specifications? Well, that is fairly simple because I'm interested to keep the model as simple as possible so that it can be explained to engineers, so people that have to deal with those issues can really work with the model. Well, this is simple because now I have introduced all the notions you need. We have, in this case, a very simple specification, just one input channel, just one output channel, X and Y. And now I do a description of the specification. I say the specification, which I call an interaction interface assertion. This specification says X has to be in the trivial relation to Y. And here is a logical description of what it means. For all possible messages in this type of messages, the number of messages in X and the number of messages in Y have to be the same. It simply means that it's a correct transmission component. It only transmits messages that it has received, and it only delivers messages that has been received, and every message that has been sent is finally delivered. And that can be expressed also in safety and liveness properties, which are just special cases of what I've written down. So it's a very powerful way of specifying behaviors. Well, now you can say, well, it's a bit strange because you don't say something about the time dependencies here. Well, this is the next interesting possibility, because now we have two ways to deal with this specification. That's what we have specified. If Y is an output history or an output stream, or this transmission component, this is just the interface assertion. And then we can add strong causality. And I just added strong causality now just as it is defined for TMC. And now we can argue with the strong causality, because this has to be true for all histories, for all streams. So we can take a stream which after T has no more messages. And taking this stream, we immediately can conclude this, which says if Y is an output history, then for each message, we know that the number of messages in Y until time T plus 1 are less than in X. And this is exactly the causality, because it just means we can only transmit messages that we have received so far. So this causality mechanism is a very nice possibility to deal with properties and to prove properties, because now we can prove properties about our system just looking at the specification. But some properties, especially in feedback loops, can only be proved by adding causality. But causality is part of the properties of the system. You can also now describe timing properties. This is a slight extension where we talk about a real-time property, where we say, I'm not going to explain the details, but the ideas are following. We say that we see the output only under a certain delay. Strong causality means there's one. A larger delay could mean there's a higher number than one. And we are guaranteed to see it after a certain deadline. So we can do a real-time specification immediately here for the system. What is also remarkable is now composition, because if we form architecture, we do composition. Architectures are easy to form. We take the systems, and if their input and output channels coincide, then we take them as shared channels, and so the communication goes over that. And so if we have two specifications, specification of system F1, specification of system F2, and we have the interface assertions here, of course we would like to get from that the specification of the system interface behavior after composing both. Well, it's important to keep it modular. Modular means that we can derive the behavior of this system, the specification of this system, from the interface specifications of the two subsystems. And in that case, it's really beautiful, because we take a logical AND between the two interface specifications, and we hide the channels, the shared channels, by existential quantifiers. It looks very simple, but it's only because we require strong causality it works. So this means now we have a very nice calculus where composition of systems is modeled by logical and channel hiding is modeled by existential quantification. So it keeps everything extremely simple. And now, of course, the next step would be, what about probabilities? Well, I could easily write a specification expressing what I would like to express, that the probability that the transmission is done after a certain delay until a certain deadline is reached is above 80%. This is something we would like to see. If you look at, we have seen already examples in this workshop, we would like to see in telecommunications numbers which are 0.999 or whatever. But if we want to really express that, of course, we have to make sure that our calculus, that our models really allow us to express that. So we generalize a bit our specification. This is exactly the slide you have seen, and I only change one little thing. I introduce a probability distribution for those sets of possible outputs. And so we get for each input history a set of possible outputs. That's the logical view. And now we get, in addition, a probability distribution over that, which tells us what is the probability of the different outputs. This is, of course, important because many times we describe systems which are non-deterministic, and where some outputs are good and some other outputs are possible but not so good. And of course, it would only make sense to write such a specification if we are able to express that the outputs that are not so good are not seen always, but only with a certain probability. Now here I have written it down a little bit more carefully. Probabilistic behavior now I take as a mapping that takes a set of input histories and maps it onto a probability distribution with the following idea. Giving a set of input history and a set of output history, now we can express a probability, namely the probability f of x with y in square brackets is the probability that the output that we receive is in this set y, provided the input is in x. So this gives a very clear idea how we model probabilistic stuff. And now I show you how to do the composition. It looks a bit terrible, but the idea is not so difficult. Given these two components for which we have description of their probabilistic behavior, we first define a function g, which is nothing than to take these components together, independent, also stochastically independently, the behavior where we have now all the channels still as input and output channels. And that's easy because this is just an independent definition of the probability. So we take just the probability for that and for that component to derive the probability for G. And based on this idea, and I should emphasize this is assuming probabilistic independence. If there are hidden dependencies, the formula would be different. Now we can define the probabilistic behavior of the composition. Now we have the composition here. F is now the behavior of the composed system. And how do we do that? Giving a set X and a set Y, set of input history, set of output histories. We consider G on X prime. X prime are all the input histories we can observe if we, in addition, look at the shared channels. And we apply it to this set. And how is this set defined? It's all the output histories, including the shared channel, where we require that X prime, there exists an X prime in our set X prime as defined here. And we require that if we restrict Y prime to the output channels, we are in Y. So we get an output in the set we require. And now this is the fixed point equation. It says that the input channels and the output channels as shared channels have to be the same. So it's just a fixed point equation. And that gives us a straightforward definition of composition of probabilistic components. And now we can model reliability and availability. These are quantitative properties. We cannot model reliability or dependability without probabilities. And so therefore, it's important now that we have this probability model as hand. So there are lots of examples, of course, how we could do that. Resource usage, system operation costs, dependability, uptime, downtime, and reliability. So I will give you now just these different possibilities to go for quantitative specifications. There is quite some work in the group of Tom Hensinger in that direction. He looks at metric spaces and at metric distances between behaviors. I give you just a simple example which we could use in our case. If we can introduce a metric on our histories for a given set of channels, and we can use the Cantor metric, which says we take the greatest lower bound of 1 to the power of 2 to t, where t is a number is a number which is required that the input and output, the prefix of x and x prime until t are the same. And this gives us one metric we could deal with. But I'm not going to deal with metrics. I use probability. I skip that. We just use classical probability theory used on measurability, and I will go over this because of time. And now we can talk about availability and reliability. What is our view on reliability? These are properties of the black box interface behavior. So it's a functional property, which is a bit in contrast to what you find in the textbooks, which always say these are non-functional properties. I agree. I claim that these should be functional properties, quantitative functional properties, and we want to quantify the amount of observable failures of the system. And of course, there are many ways to express that. And we have done some experiments, for instance, with train systems, where we are looking forward to, or did some experiments to model availability and reliability. And I have some PhDs which work on that. Let's be more concrete. What is reliability? It's a probability that the lifetime of the system is at least as long as t, or more precisely, the system works correctly at least until time t. And now we can just use our calculus. To simplify it, I took away the input histories. I just talk about a set of output histories, so giving a set y, which is a set of output histories. The first step would be, we say that an output y prime is correct if it is in the required histories. That's simple. And we can generalize to sets of output. A set of outputs is correct if it's a subset of the required outputs. And now if we have a probabilistic system behavior model, which is again just a mapping from the histories, or sets of histories, I should say, onto probabilities, then it's easy because we can now ask what is the correctness probability for y, which is the specification, and it's just the probability of y. Because this is a probability that the output is a member of y. And now we can also talk about reliability, which is just the expected value for the distribution. Here I use the distribution. This is a probability that we find an error after t steps, and we take the expected value over that, and that's the measure of the reliability. So we have done a formal model of probabilistic behavior, and over the formal model, we have defined reliability. We could also introduce other metrics, because this is a very simple thing, because now we have just used a classical notion of correctness and added probability, but of course we could also be more general. We could look at more sophisticated concepts of correctness and reliability. For instance, we could ask questions like, with which probability is the system output correct to which extent over which expected interval of time? And then we have three things in it: probability, an approximation of correctness, and an interval of time. This is the quality systematics we have developed over the years, which I will not go into details, but this was one of the motivations to be able to model a lot of those with the approach. And then the result is that if you study classifications of requirements with a system model where you have, I just take the first line, where you have a syntactic interface, a logical interface behavior, that was the one which I introduced first, and its generalization in the probabilistic interface behavior. And again, I would like to emphasize here that the probabilistic interface behavior is a conservative extension of the logical interface behavior. So we don't have to change anything. We just assume additional probabilities. Then we can start to characterize requirements. And then, for instance, reliability is a functional requirement. Safety is a functional requirement, which changes exactly what is written in the standards. Because in the standards, they say time is not part of a functional requirement. In the standards, they say these are non-functional requirements. But it has just to do what you accept as functionality. And my argument is, if you are interested to use systems, take your smartphone. It would be ridiculous to say in your smartphone reliability is not part of your functional requirement, because if you have a smartphone which never works, or only in very, very rare moments, then you would not consider this as a good functionality. So have we actually going the direction we have to change a bit our understanding of these notions? And we go into something which people have looked at for some years already ago, but didn't make much progress. And now we can go into that because now we can talk about rich interface specifications. We take a logical interface behavior, we take a probabilistic interface behavior, we write interface assertions to describe the logical interface behavior, and we introduce probability distributions or predicates that talk about probability distributions to talk about probabilistic functional behavior. And then we can write rich specification with all the stuff I have talked about. What is in particular interested, we can study and specify quality of service, which of course is in connection with communication services, with services in the interface, extremely interesting. So here my conclusion. If we want to go step by step into these cyber-physical systems, of course cyber-physical systems, they are interacting with the real world. So we have to go beyond classical functional correctness. We have to introduce probabilistic correctness. We have to introduce approximated correctness. We have to understand how all these things fit together. And we need one model in which these different notions of models and systems are collected together in a way that we have one comprehensive look at that. And it's very important because when I look back at the conference we had in Stuttgart, where a lot of people from practitioners were there, they really have trouble because they often don't understand how they bring together these different notions into one framework. So this would be a step into such a framework. And then we can express what I already said. We can express that the system produces an output that is correct to a certain degree over a certain time span with a certain probability. Thank you.
Well, let me start. So how would I use such a model in practice? I would imagine that it's extremely hard to come up with a probability for an individual component that it does something correct, let's say. And I know similar techniques from software estimations, for instance, which ultimately suffer from the fact that the underlying probability is just guesses, and then you build a lot of math on top of it, but the foundation is not there. So how you get the underlying probability?
Yeah, the first answer is a very proper, pragmatic one. If you look at how people do that construct airplanes, they have to come up with certain probabilities about the safety of the airplanes. And how do they do that? They use exactly techniques like that, also not so much formalized in one system model, so they find out what are the probabilities that some of our subsystems do not work, and then they just do rough calculations to come up with the required 2 to the minus 9 or 10 to the minus 9 or whatever they need. So I think in practice people since a long time work along that lines. So far we did not study carefully how we can have an extensive model which captures all these different aspects within one model. But you're absolutely right, because it would be very difficult also to find out. You have seen my laptop didn't work at the beginning, so what is the probability that happens next time would be very difficult to find out. But I think we need, as engineers, we need just the instruments to talk about that. We need the right notions, and even the notions are not very proper so far. And based on that notion, of course, we can do a lot of stuff. And not everything is precise. A lot of the things would be just approximations.
So would you assume that those things are measured based on experiments, or would the calculus go like all the way down to the program and the way the program executes and derive it bottom up?
I don't see a lot how they do it with experiments. It's just more experience. It starts with the reliability of hardware components, and then they know that the hardware component has a certain reliability. And if the reliability good enough. What they do is they introduce redundancy. So they introduce 3 or 4 of them. This allows you to do that completely on the logical level, and you get all the behaviors there, and then you could just take approaches like FTA or FMEA, these analysis techniques, which could work perfectly with that, and you have already a logical framework in which you can do that.
Okay. Any other questions? No? Well then, thank you very much.
Thank you.